Hi, in this video we are going to talk about red-black tree. Like AVL tree, red-black tree is also a self-balancing binary search tree. Like AVL tree, in red-black tree also we have search simple as normal BST search, but insert and delete operations are complex again. In insert and delete operations, we do some restructuring if insertion causes unbalancing or deletion causes unbalancing. If we talk about differences with AVL tree is very strict. In AVL tree, height difference between left subtree and right subtree should not be more than 1. Red-black tree is loose compared to AVL tree. We'll talk about definition of red-black tree and then we'll understand that red-black tree allows twice the number of nodes on one path compared to other path from a node to its descendant leaves. What is the advantage of being loose? In red-black tree, when you do insertions and deletions, number of rotations happen less because the rules are not very strict. So many times insertions and deletions, they fall within the constraint and cause less rotations. Now what is the disadvantage of being loose? Obviously your height may become high, your worst case height may become high, and which may cause search being slightly costly. So if you have a set of operations where you have fewer insertions and deletions and many searches, which self-balancing BST you will use? You will use red-black tree or AVL tree. Since searches are many and AVL tree has faster search operations, you would definitely prefer AVL tree. But in general, when you have a mix of insertions, deletions and searches, red-black tree is always a good option. Let us now talk about definition of red-black tree. The first point in definition is every node is either red or black. The second point is root is always black. The third and fourth point are really important. These are the points that make red-black tree a balanced binary search tree. The third point says that no two consecutive reds allowed. We cannot have a red child of a red node. Similarly, a red node cannot have a red parent. The fourth condition is number of black nodes from a node to all of its descendant leaves should be same. Let's see what does it mean. Let's consider this node. There are 5 paths from this node to all the descendant leaves. One is this, second one is this, third one is this, fourth one is this, and fifth one is this. All of these paths have same number of black nodes. This path has 2 black nodes, this path has 2 black nodes, this path has 2 black nodes, this path has 2 black nodes. If you see this node, there are 4 paths from this to its descendant leaves. And all these paths have one black node. If you see this, there are 2 paths from this to descendant leaves and both the paths have one black node. From every node to all of its descendant leaves, we should have same number of black nodes. We also call it black height of a node should be same through all descendant leaves. Now if we combine third and fourth conditions, we can notice that this is maximum unbalanced red-black tree. We cannot make it more unbalanced. For example, if I add a red node, the third property will violate, which says that no consecutive reds. And if I try to add a black node, then the fourth property will violate. Because fourth property says that number of black nodes from every path, from root to all the descendant leaves should be same. Not only from root, from every node. So if I add a black node, then this path will have more black nodes than this path. So we cannot add any more nodes on this side, right? So we can't have more unbalancing. This is the maximum unbalanced. We can add red nodes here. That will make red-black tree even more balanced, not unbalanced. I can have some nodes here as 5, some nodes here as 15. This is still a red-black tree, valid red-black tree. All the 4 properties are followed and this is more balanced. So if we consider the previous red-black tree, we can't make it more unbalanced. That's the maximum unbalanced tree, red-black tree with these many nodes. Here is one more example of maximum unbalanced red-black tree. We cannot add anything to this side. However, we can add more red nodes to this side. That will make it even more balanced. So this is maximum unbalanced. Now if you take a look at this maximum unbalanced red-black tree and the previous maximum unbalanced red-black tree, you can notice one thing, that the number of nodes from a node to its closest leaf and the number of nodes to its farthest leaf, they have this relationship, that maximum number of nodes on the path to the farthest leaf can be at most twice than the number of nodes on the path to the closest leaf. See, if you see this path, you have 3 nodes. Now if you see this path, which is the farthest path, how many nodes you have? You have 6 nodes. So this is what is balancing by red-black tree. We cannot have twice nodes, more than twice nodes on one path compared to other path to a leaf. If you compare this balancing with AVL tree, in AVL tree, we were allowed to have difference of at most 1 between 2 heights, and here we are allowed to have the difference twice. And this is why we say red-black tree is less strict when we compare it to AVL tree. When we do red-black tree insertions and deletions, this is the reason we have less number of rotations, and insertions and deletions are generally faster. In insertions, we first try to avoid rotation by doing recolorings, and if that does not work, then we do rotations in insertion operation. In this video, we have introduced red-black tree. We have talked about its properties and its applications. If we talk about practical applications, practical implementations, red-black tree is used a lot. This is the data structure which is implemented by set and map libraries of C++ STL, tree map and tree set libraries of Java collections.